G'day ladies and gentlemen, it is the Raging Ranga here. So give a cheer and have no fear. Let's grab a carbonated beverage and welcome back to our topic of differential calculus. In this video we're going to be looking at instantaneous rates of change. And speaking of carbonated beverages, don't drink and drive. We have our speedo here, our speedometer in a car, measured in, as far as I'm concerned, the proper units, kilometers per hour. America, get good. And what this shows is your instantaneous speed. Your instantaneous speed. This is not your average speed. Keep in mind that average speed would be your average speed between 2 points. If this was, say, the beginning of your trip, 0 minutes, this was the end of your trip, 30 minutes, your speed is going to be all over the place. You might start off a bit slower, then you hit the freeway, your speed increases up to here, then you're slowing down a little bit for some sheep, and then, you know, you're racing some bloke. No, you're not racing anyone, you're doing the speed limit, and then you know, you come to a stop at the end of your journey. Your average speed would probably be somewhere around about here. So the what speed you do on average over the course of a journey. Your speedo does not show your average speed, it shows your instantaneous speed. What speed are you doing at that exact moment in time? Instantaneous just means at an exact moment in time, at that very instant. And this is going to start us down the track towards differential calculus, which is finding the instantaneous rate of something. So in the last video, we talked about getting the average rate between 2 points for a varying function. We did that by picking 2 points. So if I wanted to find the average rate between points A and points B, I find what the points are, I get the slope of the line between those 2 points, and bingo bango, you've got your average rate between those 2 points. However, if I want the instantaneous rate, so I want to find the instantaneous rate at A, I can't use that method, because as you can see, this line here does not represent the slope at A. The slope at A is simply the tangent line to that point A. Now, for those of you who might not remember what a tangent is a line that just touches a slope or a curve at that exact point. So the tangent at point A is a straight line that only touches point A in this region here. And that, the tangent line, is the instantaneous rate of our function at point A. So there's your first definition right there. Get this green box down and we'll talk about it. So what do we have here? We have our function f of x. And we have our point A. The coordinates of point A will be x and f of x. So, for example, if I draw an xy axis, there's point x on the x-axis, there's point there's point f of x on the y-axis. And the instantaneous rate of change in our function at any point A is the gradient of the tangent at A. So the slope of this tangent. So basically, you find point A, you draw a tangent line through point A, and then you get the slope of that line. Possibly best described with an example. So, draw this example down and write this example down. Get this picture and write the example down. We'll give it a crack together. And you're done. Fantastic. So we want to use tangents drawn to find the instantaneous rate of change in our function f of x at a and b. Now, just a heads up that f of x will actually be represented by numbers in the near future. For example, this graph here is probably something along the lines of -1/4 times x take 2 squared plus 3. Those of you who have watched my quadratic equation videos should be able to work that out from this graph using that point. What I mean here though is that f of x is actually a set of numbers, it's a function. And so for example, this point A is actually at the coordinate 0, 2. You could plug 0 in for x here, crunch the numbers, and you'll get 2 for your y value. Point B is going to be 2, 4, 6, and then plug 6 into this equation, you're going to get -1 in the y-axis. Sorry, yeah, -1 in the y direction. But onto the actual question itself, we want to get the slope of this line here. So they've drawn in a tangent, and you'll notice that their tangent is strategically starting here and strategically finishing here. That was no mistake that it starts here and finishes here, because you'll notice that it actually intersects a nice point. So this nice point here is -2, 0. This nice point here is 2, 4. You find the instantaneous rate of change for that by doing your y step 4 take 0 over 2 take -2, which will give you a tangent of 1. So a gradient of 1 rather. So the gradient of this tangent line is 1. That means the instantaneous rate of change at A is 1. So for example, if this was your distance traveled and this was your time, your instantaneous speed at this exact moment in time would be 1 meter per second. We then look at the tangent B has a gradient of -2, so you find it in exactly the same way. You might want to strategically pick 2 points that cross grid lines, so that's a nice point. That's a nice point. Find the coordinates of those 2 points. You're going to get a slope of -2. So your gradient is -2. That means your instantaneous rate of change at point B is -2. Note that you can use any 2 points along this line. It doesn't have to be the whole length. It doesn't have to be using that point there. Just any 2 points along this straight green line, along this tangent line. I could even extend it out if I really wanted to. Any 2 points will help you get your slope. And that's it for this section, ladies and gentlemen. Give these questions a go, and we'll catch you next time. Don't forget to stay classy.